All right. So last lecture we talked about the idea of just purely rotational kinetic energy and the rotation of a rigid body, something that actually has an extension with mass. You can't treat it as a point particle. This lecture we're actually going to talk about the forces involved in actually making something rotate, and those forces are actually called torques. So if you've used a torque wrench or worked in a mechanic shop, you may be familiar with the idea of torque. So the ability of a force to cause a rotation depends on three factors. Okay, we've got one, the magnitude of the force that's actually acting on the object to cause the rotation. Okay, so we have that here with this force. We have the distance from the point of the application of the force to the lever arm. Okay, so here in this picture we have this wrench on a bolt, and obviously it's gonna, if we apply a force the right way on the end of this wrench, it's going to pivot on the bolt and pivot the bolt around. So our pivot point is down here on the bolt, and the wrench is going to act like our lever arm. So that means we do have some distance from the point of application to the pivot. Okay, so that's here. I'll label it orange. Okay, so that's going to be from the distance of the pivot point up to where that force is being applied. Okay, next we have the angle at which the force is applied. Okay, so this is phi. Okay, so notice that phi is not like theta. See, theta is actually down here. Okay, and theta is actually between the x-axis and the lever arm r, right? So that's our theta that we're used to because it's from one of our cardinal axes, x or y. But now phi is completely different. Phi actually goes through this little arm here, the axis through the lever arm, right? Phi goes from the axis through the lever arm to where the force is pointing. So what we can do here is essentially develop a definition of torque from these three things. Okay? So a force causing an object to rotate about this pivot point. Okay, so this is the force. We're going to call this a torque. Right? Okay, and then a torque does depend on these three factors. Torque is the rotational equivalent of force, okay, and it also has a sign. So a torque causing a counterclockwise rotation is positive, okay? So a torque going this way or causing a rotation this way is positive, while a torque causing a clockwise rotation is negative, okay? So you can see over here, this force is going to cause a positive torque since it's going counterclockwise. And then torque is always calculated about a pivot point. So we do have a pivot point here. In this case, it's the bolt. Okay, so we have these three factors. Let's see if we can figure out how to put them together. Now, suppose a force is applied to a bar attached to a pivot point on one side. Okay, we've got that. Here's our pivot point, just like last time. All right, and then the force is going to be applied on the other side. Okay, so the force is applied to the opposite end of the bar. Okay, and it can be applied at any angle phi. So we're not going to be picky. So we have those two components. Okay. Now there's two things, two more things, I guess I should say, that are crucial in calculating this torque, and that is a line of action and a moment arm. Okay, now the line of action, that just runs through the applied force. It's the line of action, action being the force, the thing that's causing the object to rotate. Okay, so here's our line of action. I've got it labeled here, line of action. That's the first part. That's easy and kind of obvious to see. The second one's a little more tricky. Okay, so the second one's the moment arm. Okay, and it's the shortest distance between the pivot point and the line of action. Okay, so essentially we want to draw whatever line is going to make a right angle with the line of action. Okay, so here's our right angle, and it's got to come up from the pivot point, which in our case is a bolt, or the bolt in the problem, and that is our moment arm, okay? Now I have here something interesting. I say that the moment arm, which is just d, or the length of the moment arm, I say, well, that is r sine alpha, okay? But then again, I just jump down here and I say, well, okay, well, that's equal to r sine phi. Well, you may be asking, like, what is going on here? So there's a cool trick here that we're applying. Obviously, since this angle, I'm going to switch to black really quick, okay? Since this angle here is phi, we can actually just take 180 and subtract phi to get this other side, okay? So this is 180 subtract phi, and I'm going to call this alpha, okay? So now, since this 180 minus phi is alpha, I'm going to make a statement here. I'm going to say that sine of 180 minus phi is actually the same thing as just sine of phi, which is actually the same thing as just sine of alpha equals sine of phi. Now that may seem a little weird, but the way you can think about this is simply, and I will draw it here. Okay, if we have a x and a y axis, and then some point setting up here, we have phi and we have alpha. So you'll know you know that if we take sine of one of these angles, what that's going to do is give us the height off of the x-axis of this point. Okay, so you can see that sine of alpha, okay, that's going to give me the opposite side. Okay, well, here's sine of alpha. It's going to give me that height. And the same thing, sine of phi, this trig function gives us the y-coordinate of whatever point we're interested in. Okay, so even sine of phi will give us this height here. So because either if we use alpha or we use phi, we still have the same positive y value. Now this wouldn't work if we want to do like cosine of alpha or cosine of phi. That's a different story. But at least for what we're looking at, alpha or sine of alpha or phi here is actually going to give us the same output. So that's why I have it written here. Sine of 180 minus phi is just the same thing as sine of phi. So if you're not 100% convinced, I suggest you try it a couple times, maybe draw out a picture like I did, label it, and study it for a minute. But it's a cool trigonometric trick that you can use in situations like this. So that being said, the magnitude of the torque can actually now be calculated. All right, so we're going to define torque as lever arm distance, d, times the force applied, okay? And we want the tangential component of the force. So essentially like what's making that right angle to the lever arm. So we can think about this as the tau being the magnitude of the force times r sine phi. Okay, now let's think about what r sine phi is. So if we look at it, we say r sine phi. Well, if r here I labeled in orange is our hypotenuse, so that would just be the hypotenuse times sine. Well, that just gives us the length of the opposite side. Okay, and the opposite side is d, our lever arm. You can see here in my diagram, alpha is opposite of the lever arm. So, and then if r is the hypotenuse, all this is simply d. So that's force times the distance, or the moment arm, and that's exactly the definition of torque. So that's one way to think about it. The other way to think about it is essentially where you want to get the tangential component of the applied force. So we can say, we can build this from, instead of the moment arm, we can build it from the lever arm r, okay, which is in orange here. So if we want just the tangential component, it turns out that, let's see, I'll use red. It turns out that this, if we think about the trig here, I'm not going to label it on the graph or the plot, the figure there, because it's getting kind of gross and crowded. But the idea here is that this is just the tangent component of the force, so the piece that's actually pointing at a right angle with the moment arm. Okay, so you can think about sine of phi as like scaling r to make it the moment arm, or you can think about phi as like grabbing the tangential component of the force. So that's all well and good. We've analyzed a situation where we've had one torque being applied around a pivot point, in this case, the wrench and the bolt. So the next question would be, what if we have more than one force acting? So you can see here in this picture, we've got four forces acting in really crazy directions, okay? So if we have this extended object and it's free to rotate about an axle, so you can see we do have an axle right there. Okay, if this object's free to rotate about it, and all these forces are acting, how do we come up with a net torque, okay? So the cool thing is that even though these forces may be pushing in different directions, the net torque is all that matters. Okay, so we can actually calculate a torque for each of these forces and then just sum them up. So the important thing here is that no matter what all these forces are doing, some of them may even cancel each other out. We don't care. The only thing we care about is once we add them up, that one torque left over, that net torque, that's what's going to cause our rotation. So although some of these forces may have unbalanced components in non-radial directions, the axle acts as a normal force to cancel out any translational motion of the object. Okay, now that's just a fancy way to say that, like, for example, if we were to look at force 4 here, it looks like force 4 is trying to just yank this object up to the top right corner of the slide that we're looking at, right? It doesn't look like force number 4 is actually going to cause some sort of rotation. So the point of this second little paragraph here is just to say that even if this force isn't really causing a rotation and still acting on the object, the axle is going to hold this object in place, right? So the axle is going to cancel out force number 4, since force number 4 isn't really trying to add a rotation, it's trying to like pull this object. But it can't because there's an axle through it and it's holding it in place. So that's where the normal force, so to speak, from the axle is coming from. The normal force here from the axle is canceling out anything that's not going to cause a rotation. Now, let's think about just a very natural rotation that we've actually looked at a little bit in the previous lecture. So if we had this, I think in the last lecture we had a bar that we let go and dropped and it swung down and like smacked the wall. So that rotation was actually caused by gravity. Okay, so let's think about this example here where we're just looking at rotations due to gravity doing all the work for us. Okay, so let's consider a rod with an off-axis axle such that its center of mass is higher than the axle's location. Okay, now you'll remember from the last lecture, a rotation around the center of mass makes the moment of inertia easy to calculate, and it causes some things to cancel out. But here in this situation, our axis of rotation is offset, right? So here's our center of mass, here's our axle. So what we have is we have this offset, and the center of mass is sort of stuck out from the axle a bit. Okay. So just like with moment of inertia, gravity acts on all particles in the object, okay? And it's going to exert a downward force on all of these individual particles. So if we take this big weird object, break it up into small pieces, each piece, so essentially particle I, each piece is going to be acted on by gravity. So F equals MIG. So you'll notice that F has a subscript I. Let me see if I can zoom in. Yeah, F has a subscript I because those forces may be different. Each individual piece, we know we may not chop it up evenly. So each individual piece in this object may have a slightly different mass, so it's going to have a subscript. But G, the acceleration due to gravity, they all feel the same G. All right. Now, the magnitude of the gravitational torque on each particle is going to be still a force times a length of a lever arm. Okay, sorry, the length of a moment arm. Okay, so here again, D is the moment arm. I've even made sure to mention that over here. Okay, so D's the moment arm. Now the force is obviously going to be from here. This is just the force due to gravity. So we still have D times force here. Okay, moment arm times force. There we go. Okay. Now, there's something a little funny that's going to happen here. We need to think about the sign applied to these individual particles. So we know that we have a bunch of them because we've broken up this object into lots of little ones, but you can see in the image on the top left, we're only considering two particles. Okay, we have one up here, particle 2, and we also have particle 1 here in the bottom left. Okay, now the question is, what do the torques look like on these two objects? Okay, and you can see we've got the moment arms labeled, and that's just the straight line distance from the axle to the moment arm through each torque. Okay, sorry, the line of action. Ooh, this is gonna be hard. I always get those two confused. Okay, so we do have a line of action here that goes straight through the vector and a line of action here. Moment arms are always the shortest distance between where the center of mass is, or the axle. All right, shortest distance from the axle to the line of action. Okay, and these are our moment arms. So a particle to the right of the axle will experience a negative torque. Okay, so you can imagine that a particle to the right, let's see if I can label these here. Particle to the right is wanting to spin this way, okay, and that is indeed a negative torque. Now, if we look at the particle on the left of the axle, okay, so over here, particle 1, it's actually wanting to spin in a counterclockwise direction, right? Because the gravity's pulling down on it this way. It's wanting to spin the other way. It's wanting to spin counterclockwise, which would actually be positive. So we actually have a positive torque here. Now here's the trick where the sign comes in. Okay, so the torque here in this situation is actually opposite in sign to x. Okay, so you'll notice that our origin is here at the axle, right? So here's our origin. I'm going to label this in something like blue. Let's do blue. Okay, here is our origin. Okay, that's also where the axle is. So if we move in the positive x direction over here to particle 2, so we go plus x, but like I said earlier, the torque's negative. Okay, if we move to the left, okay, so we're going negative x, even though we're moving in the negative x direction, the torque experienced by the particles over here are actually positive. So that means we sort of have like Hooke's law with the restoring force. It's always opposite of our value of x. So what I'm going to do is just add in this negative sign. So now we can actually calculate the torques on all of these objects, all these particles that make up the one object. Okay, and so we just have to think about the physics of the situation to realize a negative sign belongs in there. All right, so I can group these things together. If I group the individual particles here, I have this like negative mixi, and then multiplied by g. G is the same for all the particles. Okay, so that was just for one of them, right? In like right here, this is just for one of them, but I want to sum up all the particles that make up this object. Okay, so we need to think about the net torque from gravity. Okay, so I'm going to add my summation, and look at what this gives us. So G is the same for all of them, so I'm going to pull it outside. But look at what we have. That almost looks like the definition of center of mass, right? So center of mass, if we consider the calculation here, this is our calculation for the point of the center of mass. But look at what happens if I do this. If I write total mass times the x component of the center of mass, look at what I get. Okay, this big M and this big M actually cancel out, right? So look at what I'm left with. Whoops. I'm left with this term equaling this term. Well, I have that term right here. So what I can do is I can actually replace the summation with just big M times the center of mass coordinate. Okay, so I've done that here. So here's big M times the center of mass coordinate, and that completely replaces this summation. Just using some algebra and the definition of the center of mass allowed me to do that. So here we see that big mg is the net gravitational force on the entire object, okay? And xcm is actually the moment arm. So what that's saying is, let me use a different color. Here we go. So what that's saying is we have this net torque, okay? That's always the moment arm times force, but in our case, the moment arm is just wherever the center of mass is, right? Times the total mass of the object times g. So this is just the object's force due to gravity. So this is a neat little result. It just says you essentially take all the torques, all the gravitational torque, and then you act like all the mass is at the center of mass. So essentially, mathematically, you take all those little particles, smash them together at the center of mass. Yes, at the center of mass, and then the distance from the axle to the center of mass, whatever that is, that's going to be your moment arm. Now, what's really cool is if the center of mass is actually at or on top of the axle, above the axle, then this object's actually going to balance. So that's the whole trick to balancing is whatever the center of mass of the object is, if it's on top of that pivot point, your object balances. Okay, now here's a few more things we need to think about, but do note that torque is the rotational equivalent of force, okay? So you can think torque and force. Same thing, one's in a circle, one's linear. So how could we actually use Newton's second law to incorporate rotational kinematics and rotational dynamics? So let's see if we can take Newton's second law and sort of tweak it for a rotational situation. So all points in a rotating object, they have the same angular acceleration. Just like in the previous lecture, we talked about how all the points in an object have the same angular velocity. Same thing, same angular acceleration. Okay, and we do know that the angular acceleration is related to the tangential acceleration just by scaling the angular acceleration by the radius or the distance from the point of rotation. Okay, so we can actually rewrite Newton's second law. Okay, so instead of F equals ma, okay, well, F equals ma would be for a tangent acceleration. So let's replace that tangent acceleration. Okay, so we'll actually replace that with r alpha. All right, so if we multiply both sides by r, something really cool happens. Okay, so we're going to multiply both sides by r. So this side gets an r. This side will get another r, making it r squared. Okay, now look at what we've done. We've just taken Newton's second law and slapped an r on each side. And now we've turned it into the definition of torque. We have some distance times a force. Okay, and that's actually where we're going to get the torque from Newton's second law. So if we rewrite this and just say that RF is equal to tau or torque, then this is mr squared equals alpha. Okay, so this is how we can actually start with Newton's second law and generate sort of a Newton's second law for torque. So here we see that torque causes an angular acceleration, and we see that because angular acceleration is actually right there in the equation. Okay, so if torques acting on all the pieces of an object are summed, so on the previous slide, we had a single torque, which was equal to this statement here. Now, if we wanted to talk about the net torque, we add all these up, okay? So if we're talking about the net torque on an object made up of a bunch of little pieces, this is what we're going to come up with. So if we sum these up, this should look really familiar, okay? Because you'll remember that this is just the moment of inertia. If we sum up all those little pieces of an object, right, according to m times r squared, that's just the moment of inertia. So this is going to replace mass in Newton's second law. So if we rewrite this and just plug in the moment of inertia, here's what we get. It's really simple. It's just tau net. So the net torque is just the moment of inertia of the object, right? So all those little pieces added up, all those little moments of inertia added up. So just the moment of inertia of the object times its angular acceleration, that's going to tell us what the net torque is. Okay, so if the net torque is 0 Newton meters, then an object is either not rotating or it's rotating at a constant angular velocity. And you'll remember that from Newton's second law. If Newton's second law is F equals ma, but you sum all that up and it equals 0, an object is either not moving or moving at constant speed. So it's very similar. Here I've included a table that sort of drives this point home, but we have linear dynamics over here. So a force in linear world is the same thing as just a torque in rotational world. We have a moment of inertia, right? We've said that's sort of like the mass as far as like, you know, if something is hard or easy to rotate, if something is hard or easy to push, force or mass and moment of inertia are similar. We have accelerations. Well, this certainly makes sense. A linear acceleration is kind of the same thing as a rotational acceleration, an angular acceleration. And then we have Newton's second law. So over here we have A equals F over m, or F equals ma, depending on which way you want to write it. Okay, and that's very similar to torque, or tau equals I alpha. So there's a direct relationship between Newton's second law and torques. Okay, now we'll actually get really close to starting to do some calculations here. So when you're solving rotational dynamics problems, you should model and draw the object as a simple shape. I think in one example we're going to look at, we're actually using like an airplane propeller. So in that, just a rod, very easy to deal with. So model these as simple shapes. You want to identify the axis of rotation because a lot of your measurements are going to come from that point, the pivot point of the axis of rotation. Okay. You want to identify all the forces that are causing the rotation and their distances from the axis of rotation. Okay, so once you have the forces and their distances, now you can calculate all the individual torques and make sure their signs are correct. Remember, sometimes we have to think about the physics of the situation to get the correct sign in there. And then next, we'll just apply Newton's second law or the torque calculation. So in some cases, linear motion may be translated into rotational motion. So if we consider a rope across a pulley, which we will later, but the idea is essentially if we have like a rope being pulled down on a pulley, we have linear motion here, but that's going to inform and sort of control the rotational motion here. So we sort of have two different problems going on that are connected literally with a rope. Okay, so in this situation, you'd see that the velocity of the rope, or the velocity of maybe if there's an object hanging on there and it's falling, the velocity of that object would equal the tangential velocity of the spinning pulley, or the acceleration of the rope would equal the tangential acceleration of that pulley as it's speeding up. Okay, in cases of static equilibrium, this is a case where all the net forces and net torques are zero. So just like Newton's first law, there's nothing that's, even if there's 1,000 forces, they all cancel out. 1,000 torques, they all cancel out. So this is actually an entire branch of engineering called statics. You'll see if you're a civil engineer. Basically, it deals with buildings, dams, and bridges that are in total static equilibrium. It's things that aren't moving, things that aren't rotating. So the cool thing is with a net like equilibrium problem where there's no torque, there's no net torque about any point. So since there's no rotation, you get to pick where you put your pivot points since there's no rotation anyways. So when you actually analyze these static equilibrium problems, you want to model and draw the object as a simple shape. That's usually how it goes with these rotational problems. You want to include all the forces. Okay, and then you can pick any pivot point since the net torque is zero. So we can put a pivot point wherever we want to. The last thing would be to determine the moment arms of all forces about the pivot point, and then the signs of their associated torques. Okay, so we want the moment arms of all forces and the signs. So note that if you're clever about where you put your pivot point, you can actually cause some forces that have zero torque, and that'll simplify the problem. And we'll do that shortly. So the last thing to think about as far as new material is just the idea of balance and stability. So if we have any extended object that's sitting on the floor, maybe a box or something, it has a base of support on which it rests in static equilibrium. So you can imagine this car over here in complete static equilibrium. Here's my poor attempt at drawing a car. The base of support is right here. This the distance between the two wheels. Okay, so that's the car in static equilibrium. Now, if the object is tilted, one edge becomes a pivot point. Now, if we look at figure A here, okay, we got our base of support labeled, but we also, since this thing's starting to rotate, we get a pivot point. Okay. If the object's center of mass remains over the base of support, then gravitational torque, which we talked about, the whole idea of like mass collapse down to the center of mass, right? And then it's the center of mass there. That's where we're going to do our mathematics from to calculate that gravitational torque. Okay, so if the object's center of mass remains over the base of support, gravitational torque will rotate the object back to equilibrium. So you can see here, this car is clearly not going to flip over in this picture because gravitational torque is going to pull it back down to the base of support. However, if the center of mass goes outside the base of support, the gravitational torque causes a rotation in the opposite direction. So as soon as you get over that pivot point and outside of the base of support, your object is essentially going to flip over. So you can see there's my pivot point. My base of support is gone pretty much. It's up this way. So here you can see that this car is going to flip because the center of mass is outside of the base of support. So you might be wondering, how does the balance actually work? So there's actually a critical angle. I called it theta sub c. If you can reach this critical angle, which essentially is where the center of mass is directly over the pivot point, then there's no net torque and the object will balance. Okay, so this is the formula for the critical angle. You can actually, I think it's derived in your textbook if you're curious as to where it comes from. This is a bit of an extra, so I'm just going to give it to you, and that way you can have it in your back pocket if you need it. If you're curious about where it comes from, I would check a textbook. But here, T is essentially the base width, and then height is the height of the center of mass. Oops. So you can see these labeled here. Okay, so here's the base. Notice only like half of it's labeled T over 2 because we're only looking at the distance to the center of mass. right? And then we also have the height here. Okay, so that calculation will give us the critical angle. You'll notice that the center of mass is actually right over the pivot point, and that's going to cause the car to balance. Okay, now we went through that pretty quick, but I wanted to get to these examples. So I've got 3 different examples here. It's pretty inclusive. So here we go. So for the first one, we've got the engine in a small airplane is specified to have a torque of 60 newton meters. Okay, this engine drives a 2 meter long, so roughly 6 foot long, 40 kilogram propeller. On startup, how long does it take the propeller to reach 200 RPMs? Okay, so we want to know how long it takes to go from 0 to 200 RPMs. That sounds like some acceleration problem, right? Because we're going from rest to some sort of angular velocity. Sounds like angular acceleration to me. Okay, so as always, I have everything drawn out. I cheat because I use diagrams that are already made, but I do have everything drawn out and labeled. So we have this 40 kilogram mass, and then the length of it is 2 meters. So from here, what we want to do is do note that the axis goes through the axis is through the center of mass, so that's going to make things a little easier. We need to find the moment of inertia of this thing, because what I want to do, the way I want to approach this, is actually use the torque equation and then solve for alpha. So we know what the torque applied is, right? It tells us in the problem that it's 60 newton meters. So I want to solve for alpha and just divide the torque by the moment of inertia. But I need the moment of inertia, so we'll calculate it. Okay, so for a rod, and I'm just getting this from the previous table, right? That has a list of all of the, I think it's from the last lecture, all of the moments of inertia. So for a rod with the axis of rotation through the center, the moment of inertia is 1/12 times the mass times the length squared. Luckily, I have all these values, so I'll plug in my mass, I'll plug in my length, and it turns out that the moment of inertia for this thing is actually 13.33 kilograms times a meter squared. Okay, well next I can actually just go ahead and calculate the acceleration. So I plug in that moment of inertia, and then I plug in my torque, which was given to me already, and it turns out the acceleration of this thing is roughly 4.5 radians per second squared. Okay, now that doesn't tell us what we wanted to know. We wanted to know how long does it take to get to 200 RPMs. Okay, so now we need to use this acceleration to finish out the calculation. So you remember that angular acceleration is just the change in angular velocity over the amount of time it took to do that. Okay, so all I want to do here is just solve for delta t. That's what we're after. Now from here it's going to be quite a simple physics problem. Okay, so it's just the change in omega. Well, we know it starts from rest, so that's just 0 radians per second. And then we just plug and chug from here, and it turns out we get roughly 4.6 seconds. So this is about how long it takes to get to 200 RPMs. Now at the very end, we just need to assess and make sure that this seems reasonable. I think it is about 4 or 5 seconds for it to get to 200 RPMs while it's spinning up. Sounds right. So the effects of friction and drag, they cancel out the torque when full speed is reached, right? Because the net torque would be 0 because it's spinning at the same speed and not spinning up anymore. It's reached its maximum speed. Okay, let's look at yet another example. Okay, so this one is one of those where we have a linear situation going on that's sort of driving the rotational situation. So we have a 2 kilogram bucket attached to a massless string that's wrapped around a 1 kilogram 4 centimeter diameter cylinder. Okay, so the cylinder rotates on an axle through the center. And if the bucket is released from 1 meter above the floor, how long does it take to reach the floor? So the idea here is that we have acceleration due to gravity is not only does it have to pull the bucket down, it's also responsible for rotating the pulley, okay, the cylinder. So the force due to gravity is having to do two different things instead of just pulling the bucket down. So the acceleration, we expect it to be a little bit smaller. Okay, so here's my setup. I've got a picture drawn, and then I've got something a little more technical. I have essentially a free body diagram with all the forces acting on this thing. So we have the cylinder, we've got the normal force up, we have gravity down. We know that those are canceling out because the cylinder is not moving. Then we also have tension here on the edge, which is causing that rotation. And of course, tension is also on the bucket pulling up. We've had these problems before where two different parts of the tension are actually connected. Then we also have the force due to gravity pulling down on this bucket. Okay, so assuming that the string is massless, which we've done plenty of times, and it doesn't slip, we're just going to say that the tensions that we labeled here separately, TB and TC, they're actually just going to equal each other. Okay. So now let's first apply Newton's second law to the linear part of the problem. Okay, we'll apply this to the bucket. Now we know that it's going to be accelerating, and we know we have tension pointing upward in the positive y direction, but we also have gravity downward in the negative y direction. Okay, these things are going to equal MAY. Okay, and that's the linear part of the problem here. So the bucket applies a tension force to the edge of the cylinder, making the moment arm just R, right? So here's our moment arm R. All right. So this torque causes a counterclockwise rotation. So the torque is positive since it's a counterclockwise rotation according to our picture. So for the cylinder, okay, so that was everything in the linear direction. Now let's look at the rotational direction, the rotational part. So for the cylinder, we have this torque going on. Okay, we have our RF sine theta. Okay, well, we know what R is because the moment arm is just over to the edge. So it's just going to be the radius of this thing. And we know what the force is. So here's our moment arm. We know that the force, well, that's just tension, right? At a 90-degree angle. So that's going to make this a little easier because the sine of 90 degrees is just 1. And this force is always going to be at 90 degrees, right? Unless the bucket's swinging, which would be a really gross problem. So it turns out that the net torque is just the tension times the radius of the cylinder. Okay, well, we can plug that into our calculation for acceleration, right? We want the acceleration so we can get the amount of time it takes for this bucket to drop. Okay, well, the torque, like we just calculated, is just the tension times the radius. The moment of inertia for a cylinder as it rotates about an axis through its center, well, from the chart that we're going to use a lot, that's just 1/2 mr squared. Okay, now we can do some simplification, and it turns out the acceleration is just 2t over mr. Okay, now since the string doesn't slip, now we're back to the linear part here again. Okay, so since the string doesn't slip, we know that this negative acceleration, right, because it is pointing in the y direction and it's down in the y direction, we know that this linear acceleration downward is negative, and it's going to equal the tangential acceleration. Okay, so here's the linear part, and then here's the circular part. Okay, now we know that this tangential acceleration and this linear acceleration are going to equal. We can rewrite the tangential piece as just alpha times r, because r is the radius and at which point this force is acting. So it turns out we can solve for ay, for the linear acceleration, and that's just going to be negative alpha times r. Okay, we can now combine linear motion of the bucket with the rotational motion of the cylinder. Okay, so we've been dealing with these pieces separately, linear, then rotational, linear, then rotational. Now we're going to smack them together. Okay, So here I have my linear acceleration equaling negative alpha times r. Well, we have alpha, right, from our previous calculation. So we can just plug that right in and simplify a bit, and it turns out our linear acceleration is just negative 2t over m. We have that right there. Okay, well, let's see. What we can do is solve for t, okay, which is just some simple algebra, and then plug that into Newton's second law equation, okay? So that's going to go in right here, because remember, this was just t when we wrote out Newton's second law, but now we actually have an expression for it. And notice that it has the mass here of the cylinder. So we have this rotational piece inside the linear Newton's second law. Okay, now we're going to simply just solve for a sub y, which is just some algebra, and that's going to give us an acceleration, a negative acceleration of negative 7.84 meters per second squared. Now that's a pretty complicated problem. There's a lot going on, but just be aware that sometimes you have to jump back and forth between the linear part, the rotational part, back and forth until you can actually combine the two, and then you can solve for the variable that you're interested in. Okay, so from basic kinematics, we know that the change in height is just 1/2 at squared, or a delta t squared. So from our first week of this course, we can see that we simply just solve for delta t and then just plug and chug. And it turns out it takes about 1/2 second for this this bucket to fall. Okay, so with the cylinder present, the downward force of gravity must accelerate the bucket and rotate the cylinder. That's why the acceleration is not negative 9.8. It's a little bit smaller because it's having to do double duty here. Okay, so this last example, I'll walk through as quick as I can, but you'll have a lab that's similar to this, so do pay attention. Okay, so Adrian, who's 50 kilograms, and Bo, who is 90 kilograms, are playing on a 100 kilogram rigid plank resting on 2 supports. If Adrian stands on the left end, can Bo walk all the way over to the right end without the plank tipping over? So the idea here is if we can sum up all the torques and it equals 0, perfect. He's going to be able to walk over to the other end. But if we sum up the torques and they don't equal 0, it's going to tip. Okay, so here's my picture, and then I've also included this free body diagram where I have I've got the weight or the force due to gravity on Adrian. I've got the force due to gravity on Bo. I also have the force due to gravity on the plank itself because there's 3 masses in here, and then there's 2 supports, which means there's going to be 2 places where the normal force is present. Okay, since we are considering oh, good grief, there we go. Okay, so since we are considering the system to be in equilibrium, we can choose any pivot point we want. Okay, so what I'll do is I'll pick the left support, and that will remove all the torques from this normal force. Okay, so here I'm going to pick my pivot point. I could have picked the other one if I wanted to, it'd be fine, but this will cancel out the torque from the normal force 1. We still have torque from normal force 2 though. Okay, so now that I've got my pivot point picked out, we want to sum all the forces. Now we have to be very mindful of the signs, okay? So let's carefully do this. No, I want this one. Okay, so we have a positive torque, right? Because that's going to give us a counterclockwise motion. We have a positive torque from Adrian. We have a torque of 0 from the first normal force. So I'll put it in red. I'm going to go ahead and mark it out. We don't care. We also have a negative torque from the center of mass of the plank itself. We have a positive torque from the second normal force. And then we also have a negative torque from bow. Okay, now we can actually plug in what we know about these torques. We know it's going to be the lever arms, right? So dA, dm, d2, dB. We also know it's going to be their weights, right? Their forces due to gravity, because that's the only forces providing these torques. Okay, so here's our mg. There's an mg in there, but right now it's just listed as normal force. Okay, and then mbg. Okay, well, we can go one step further. Okay, we can take that second normal force and actually write it out in terms of masses and gravity. Okay, so everything else is just going to come along for the ride. This comes down, this comes down. Our lever arm, or our moment arm, comes down. But now remember, the normal force is going to be the total mass that's included acting on this support times gravity. Okay, so we have the mass of all three objects, Adrian, Bo, and the mass of the plank. Okay, so that's all wrapped up in the normal force, and then that's also multiplied by gravity. And then again, we have this term coming down where we have the distance of the length of the moment arm, and then just the force due to gravity. Okay, now what I'm going to do is I'm going to go down one more step. I'm going to just pull out G because they all have a G term in them. Okay, so I pulled that out. And now we should be good to go. I'm just going to plug in all these values because I know them. And I'm going to see what we get. So it turns out, after I plug in all of this and carefully do the calculations, I get a negative torque of negative 588 Newton meters. So Bo cannot. Yeah, so if Bo could stand on the end, this equation would equal 0. But since it doesn't equal 0, he would tip it. So he actually can't stand on the end. So those are the 3 examples I wanted to walk through. I tried to leave out as much of the algebra as I could, just sort of walk through the main parts of the math and the main parts of the problem. So if you do have any clarifying questions on these, please let me know. Otherwise, that's pretty much everything on torque. In the next lecture, we're going to actually talk about calculating it with a cross product. And then we'll finish up with the conservation of angular momentum. And that'll be it on rotational dynamics.